Welcome and hello. This is a video lesson in the FHWA hydraulic toolbox. In this lesson, I'll be talking about the channel calculator tool. All right, so if you want to follow along up on the screen here, I have the FHWA hydraulic toolbox added and loaded and ready to go. I'm going to rearrange a few things here. Okay, over in the left panel, this is the Project Explorer. You can go right click, New Channel Analysis. This is how to open up the channel calculator tool. You can also go up to Calculators and New Channel Analysis. So now I have two. That's twice as many as I need, so I'm going to delete the second one. Oops. Okay, I guess I can add another one like that. Duplicate. There's a delete. Okay, let's delete that one. All right. Now to open up the tool, you're going to go right click and then channel data. This is going to open up our channel analysis dialog box, but I'm calling this lesson channel calculator. This channel calculator is in page, let's see here, page 3 of the user's manual is the table of contents. And then the channel calculator tool we're talking about here is chapter 5, page 17. Go ahead and click that. And then boom, this is the interface we're going to be discussing in this lesson. All right, so here it is. The channel calculator can compute the full range of hydraulic parameters at a single steady state cross section in a uniform flow condition for various shaped cross sections. So some of the advantages of this tool is that it is quick and easy to use. It's easy to understand. Hopefully you'll agree with me on that when we're done with this lesson. One of the disadvantages is, just like I said, it's only for steady state uniform flow conditions and for a single cross section. All right, so if you happen to have multiple cross sections, you can add multiple channel analysis in your project in this left panel. Well, let's just go ahead and demonstrate one channel right now. So at the top, this is where we define the shape. It says type in this dropdown, but shape is sort of what it's defining. Trapezoidal, rectangular, triangular, circular, or cross section. Cross section here basically is a user-defined cross section, which we'll talk about a little bit later in the video. All right, so if I click on trapezoid, for instance, now I have to input the different data parameters that define that cross section, such as the slide slopes and the base width. If I happen to choose rectangular, there we go. No side slope, it's just the base width. For triangular, it's just the side slopes with no base width. And then what's next is circular, that is only the diameter. All right, so for cross section, like I said, you click on this define button and then you can do a user defined cross section. Let's just go ahead and mess around with trapezoidal first. With trapezoidal selected, I also want to change my units to US customary units. See, right now my default is metric units, why I have length of meters and the flow rate in CMS right here. So real quick, I'm going to just click OK, change my unit system to US customary, and then let's go back to right click, channel data. And now you can see that the units are now in feet and in CFS for the flow rate. All right, let's go ahead and add some numbers here. I'm going to say it's a side slope of 1 to 1 for both the left and the right side slopes. The channel width, I'll say that's 5 feet. Longitudinal slope, I'll say that's 0.5%, 0.005. And then Manning's roughness, I'll leave that at 0.015. All right. Down below that, I have the option to set either the flow rate or the depth, the normal depth. And I'm going to start with the flow rate of 10 CFS. Click on calculate, and then boom, over here in the right panel of the dialog box, we have all of our results. Now, we already said 10 CFS was a fixed flow rate, so that's really not a result. But then everything else should be here calculated. So the normal depth would be 0.47 feet. The area of flow is 2.592 feet squared. And then you can read all of the parameters, such as average velocity is 3.859. Froude number is just above 1, so we're super critical, but we're fairly close to the critical depth of 0.483 because we're at 0.473. That's the calculated depth right here. Let's increase the flow rate to, how about 50 CFS? And then I click on calculate. Boom, we have new numbers. Now the depth is 1.227 feet. The velocity, this is the average velocity, is 6.541 feet. And Froude number is 1.138 feet. So we're definitely super critical. We can also click the plot button, which is down here. So if I click that, we see a cross-section view of our trapezoidal channel. And if you wanted to set the properties of this plot, you can do a double left click set the properties. I'm going to talk about this in a later lesson, but just let you know that double clicking on the plot will bring up this properties menu. All right, so that is the cross section. Let's close that. Say, for instance, I wanted to change any of my input parameters. You can do that and then click calculate again, and then you'll get a new set of results. So instead of a 0.5% slope, what if we had a 0.2% slope, 0.002? If that's the only thing I change, then we should see new numbers when I click on the calculate button. All right, now the depth is 1.598 feet. That's deeper. And then we also have an average velocity of 4.742 feet per second, which is slower than it was at the steeper slope. That makes sense. And now our Froude number is 0.737. So that is now subcritical flow regime. So that tells us that the critical slope is between 0.002 and 0.005, which we actually have that right here. 0.0038 is our critical slope. So I'm not going to go through and analyze every single parameter here. We have some critical parameters. We have some shear stress parameters. As before, we can click the plot button, and then we see our depth is now up to about 1.6 feet, whereas before it was not quite as deep. And besides changing the slope, like I said, you can change other parameters as well. Say, for instance, our base width was not 5 feet, but 4 feet. That's probably going to increase the depth from 1.598 to 1.786. So you can see how this is meant to be a very quick and easy tool just to do some simple calculations for steady flow in your cross sections. All right, so let's go ahead and toggle on the depth. Right now at 50 CFS, we have a depth of 1.786 feet. But if I wanted to specify the depth and calculate the flow rate, we can do that just by selecting this radio button for enter depth. Say we want it to be 1.8 feet. And now we know the flow rate's probably going to be a little bit more than 50 CFS. So I'll go ahead and click on calculate, and it's 50.722. Again, we have new numbers over here to the right. Let's click on, how about 2 feet of depth? Click on calculate. Some of these calculated numbers are nice and round numbers because of the dimensions of 2, 12, 8, and so on. We're definitely subcritical. And then here is the plot with exactly 2 feet of depth, where the flow rate was calculated based on the entered depth value. For this flow rate or depth that's selected, that will serve as the y-axis if we click on the Compute Curves button, and then the x-axis will be any one of these values here. So because I have Enter Depth as my selected radio button, that's why it's selected here as the depth. But if I entered Flow for this radio button, if I selected that, I would see Flow up here in the y-axis. Okay, so let's just go ahead and select depth versus flow. See, we have flow as an option because it's not selected here. This is our typical rating curve. So I'll click OK. It brings up another plot, which again shows us our horizontal flow versus our vertical depth. This is your rating curve. And then if I wanted to click on compute curves and instead look at the depth versus maybe the average velocity, and then click open, that brings up that plot, velocity versus depth. Instead of a convex curve, it's now concave. And then let's see, if I do the same thing, but change the number of points to something more or less than 10, let's be real coarse about it and just say 4. Boom. Okay, so this is just 4 different data points. But if I wanted it to be more smooth, I could add more, say 40. And then let's just go with depth versus average velocity. This should result in a smoother curve. With this plot as well, you can double click and customize the plot properties. But again, that's going to be probably for the next lesson, and I'll go ahead and close that. All right, next I want to talk about the other types or different shapes. So rectangular, we've already seen these. The one particular that I want to focus in on is cross section. So this is a user-defined cross-section channel that you can just create yourself. So if it's not some sort of predefined box culvert shape or channel that has fixed dimensions, but rather it's a like a river channel that you just measure out using surveying equipment or bathymetry data, go ahead and click on define. And now we can specify the slope of the channel. That's the longitudinal slope. And the number of cross-section points for this table down below here, which is where we define the station, elevation, and Manning's and roughness coefficient for the cross-section itself. So what I'm going to do is stick with the same channel slope of 0.2%. The number of cross-section points I'm going to say is 6. So when I enter 6 here, I get 6 rows in the table. And then I'm just going to manually enter my data. So I'll say every, say, 3 feet apart, I'll have a new data value. So let me just enter this data there. For elevation, I'm just going to make this symmetric. Okay, there we go. And then for the Manning's N roughness coefficient in the far right column, I'm going to say 0.035. And I can enter that in every time, or if I wanted to just copy a value down, you can just grab this lower right corner and drag. Okay, that's what I think it's telling me. Third time's a charm. There we go. All right, so it takes a little getting used to, similar to Excel. So arrow down takes you down, tab takes you to the right, shift tab takes you to the left. And yeah, if you wanted to preview the cross section that of the data you just input, click on the plot value right here. Boom, this black line represents the topography, and then the red line is for the right vertical axis. That's the Manning's N value. You don't have to plot the Manning's N value. You can check that off, click on plot. Boom, here is the cross section. So nice to have a quick visual check, especially if you have, 10 or 20 or 50 different data points. This is rather simple and also symmetric. And then as for this Manning's N, you'll notice that we only have 5 values. There's no value here. So that's because this Manning's N roughness coefficient applies to the cross section between 0 and 3 feet. And then 0.035, this value right here is between 3 feet and 6 feet, and so on. If I wanted to make a slightly lower Manning's N value for that section at the very bottom of the channel along the invert, I would just change this number here, click on the checkbox to plot Manning's N values, click on plot, and now you see a slightly lower Manning's N value here denoted by the red line for just those middle 3 feet of the cross section from 6 to 9. This is the cross-section stationing. All right. So as far as data input goes, if you have a ton of data, you can also just paste it in. So I'm going to reset all the numbers here to 0. And then, so for instance, over in Excel, I have the exact same data. I'm going to highlight, Control C to copy, move that out of the way, and then just select the first cell, Control V, and then those same numbers paste in here. And then I can confirm by plotting that cross-section data. All right, I'm going to make everything 0 one more time and now address this import button. Browse for an existing .tw file, which I believe is tailwater file, but the user's manual doesn't say anything about this .tw file. So I'm going to briefly describe what I know about it for just to give you a head start in case you're interested. So what you do is go ahead and click on the button to browse for an existing .tw file. I have a file here, which I created before this lesson, and here it is. The longitudinal slope I added to line 5. The number of rows to define the cross section is line 9. So I have 6 rows. And then here are the elevation values, basically the next 6 rows. And then the following 6 rows are the station values. So I'm going to save this file and then browse to it and select it and show you what pops up. And then here it is. Okay, so the same numbers popped up before. The Manning's N value, the coefficients here, I wasn't able to figure out where in that .tw file I was supposed to put those. So if someone knows, let me know in the comments. But anyway, you could just go ahead and manually type those in, I suppose. Yeah, that's the best I can do without any instruction from the user's manual. So I'll just go ahead and type 0.035 in here. Just go copy, paste, 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 paste. That's also a way to do it. And then click OK. All right, so we have our irregular, or I should say, custom user-defined cross-section. We also need to put in the slope, so we'll just leave it at 0.002. And then just as before, we can enter the flow rate or the depth. We'll go with 50 CFS again, click on compute, and then here are our values using the user-defined cross-section. All right, well, that's it for this lesson. What we talked about was the channel calculator tool in the FHWA hydraulic toolbox.